So my project was sequencing songs for crossfading. Given a playlist of songs with their tempo and their key, I wanted to find out what is the best order in which to play the songs so that each transition is as smooth as possible. Crossfading is when one song fades out while another song fades in. Transition sounds good when tempos between the songs are as close as possible and the keys between the songs are as close as possible. But one of the things that I've always wondered is, how do you decide the transition sequence? How do you decide the order in which to play the songs so that you are minimizing the cost to go from one song to the next? And at first I thought this is going to be simple. You just find the next closest song. Well, that's easy until you get to the very last song and you want this playlist to loop and you want the last song to fade into the first song, and you're left with something that's awkward or clunky. My motivation for this was, I listen to a lot of playlists and a lot of mixes and whatnot, and sometimes there are just bad transitions. And that will ruin the entire playlist, the entire mix. It'll just make it sound clunky, awkward. If tempos are out of sync, if the keys are entirely different, it just sounds dissonant, it sounds bad. Other motivation, I wanted to be able to use this to create my own playlist with seamless transitions that sound as smooth as possible. Even if the algorithm doesn't decide the transition points or how to fade the songs in and out, how long the crossfade should be, it still will generate an order in which to play them. Another reason why I thought this problem was interesting and why I wanted to solve it was the way I approached it is an instance of the traveling salesman problem, which is a whole family of problems. This solution could be used to solve all sorts of similar problems. Also, it intrigued me because traveling salesman problem does not have the perfect optimal solution that can be found in polynomial time. The brute force algorithm is found in n factorial time, because if you have this playlist of songs, there are going to be n-1 factorial ways of organizing that entire playlist because it is being played in a loop. I found some related works which were very interesting, very informative. I found a Spotify paper that was solving the exact same problem, and they had the same approach that I thought of, which was to graph the songs out on an XY plane. On the Y-axis you have the tempo of the song, and on the x-axis you have the key, and the key is going to be organized by the circle of fifths. There are also heuristic solutions which will solve traveling salesman problems in polynomial time, but they don't always produce the optimal results. Sometimes they'll produce suboptimal results, especially for large data sets. But these heuristic solutions often work on these small data sets, small input sizes. So because of the way I graphed the songs, because I used the circle of fifths to organize the keys, it's not as simple as just graphing it on a flat 2D plane. In reality, you're going to have the right edge be directly connected to the left edge. So paths can go off the right edge and wrap around to the left, and vice versa. They can go off the left and wrap around to the right. And that adds a whole layer of complexity to the problem. So instead of looking at a flat piece of paper, you're actually looking at the outside surface of a cylinder. There were a few pieces of information that I did not get from the research that I did. For example, the Spotify paper, it described their approach, but it did not describe the algorithm that they chose to find the shortest path. Instead, their focus was more on picking the transition points of the song, which was not part of the scope of this project. The heuristic solutions I found for the traveling salesman problem, they didn't have the wraparound edges. So with their solutions, they were just dealing with a flat two-dimensional space, trying to find the shortest path. Also, I wanted to find a more novel solution. I didn't want to just implement someone else's algorithm into my own project. I wanted something that was genuinely mine, genuinely unique and novel. So the algorithm I came up with is a greedy algorithm of sorts. So you start with just 2 points and an edge connecting the two of those points. And then you add points to that graph one at a time, and you stretch the closest edge out to connect the new point. What this does, always stretching out the closest edge, is it's going to prevent edges from overlapping. Overlapping edges are a sign of an inefficient graph. If there are edges that intersect with one another, there's going to be a shorter solution to the problem. And then what we do is we repeat the process over multiple initial conditions to generate different results, and we take the global minimum that we find, and then we return that. The time complexity of the algorithm can be broken down fairly simply. First thing, you iterate over all vertices v in v minus s. It's going to loop n-1 times. Then for each of the v's, it will iterate over all vertices u in v minus the set sv. That'll loop n minus 2 times. And then for each u, it's going to find the closest path in P. Now, the number of paths in P is equal to the number of vertices in the path. So you start with 2, and then for each time you add a u, you increase the number of edges by 1. So if you're finding the closest path, the first time it loops, it'll be 2, then 3, then 4, then 5, then 6. And then what you end up with is the sum of the first n integers minus 1. The total time complexity of the algorithm is theta n cubed. So here's an example use case of the algorithm. You start with the input graph on the left, which is a fully connected graph. It's symmetrical, and you can see the cost of going from one node to the next. And then you just look at the points. You start by selecting a point S. This can be any arbitrary point. You start by connecting V and S, and you have 2 paths that connect the two. Then you select U, and then you find the edge in P that is closest to U. Then what you do is you stretch out that edge so that it includes U. And then you continue to repeat that for the next U. You do the exact same process. You're finding that closest edge and you're pulling it out so that it connects the next vertex. And then you repeat it finally for the last U. That will give you a complete graph. And then you repeat this over all other values for V. In the graph on the right, you can see I chose V2 as V, and then you would repeat the process again for V4 and then V5, and then once you've gone through all other values for V, you return the minimum of this graph. Now in all the cases, it found the shortest path. The output of the algorithm, we expect the result to be suboptimal because it's making a lot of assumptions. It's not taking every possible combination into account. Even though this algorithm's output is suboptimal, we know that it's better than a random path because there are no crossing edges. To have intersecting edges, that would require stretching out an edge that isn't the closest to the point you're trying to connect. And since the algorithm chooses the closest edge, which in this case is the red line, you know that it won't result in an intersection. So the implementation of the algorithm, I measured the results in 2 ways. The first way I did it is I inputted data associated with an already solved traveling salesman problem. I then compared the algorithm's output with the known solution to the problem. The largest data set I tested was n equals 26. For n less than or equal to 15, I got near perfect results. I tested 8 different data sets that were size n less than or equal to 15, and only one of them produced a path that was longer than the actual shortest path. And it was only 0.03% longer than the optimal path. But for all other tests, n less than or equal to 15, 7 of the 8 tests gave the most optimum path. But then for larger values of n, the results became less and less optimal. I also measured the results of the algorithm based on subjective analysis of the playlist generated, and I noticed that when I used my algorithm to generate a playlist, the neighboring songs were more compatible, versus with a randomly generated playlist, the 2 neighboring songs were not very similar. The input for my algorithm is a JavaScript file in which the song array is initialized with all the song objects. Each song object has a title, it has a key, and it has a tempo. So here you can see a test run of the algorithm. It displays the shortest found path so far in red, and it shows the paths that it's trying to connect in the faint white lines. And as you can see in progress, it's working on it. It's got the faint white lines showing the paths that it's trying out. And then after termination, it just has a red line. That is the final path. That means it's done trying to find other paths. I took data points for n ranging from 1 to 30. The actual time supports the results I found in the theoretical analysis. So some of the results of the algorithm as a whole, I found difficulty calculating the distance from a point to the closest edge. The reason why it was difficult to find this is because the path can go across the right edge and loop back around to the left edge and vice versa. It made it a lot more difficult to find the distance from any given point to an edge. So instead of trying to find the exact distance, I found a formula that approximates the distance. Because of this difference in the approximation and the actual distance, slightly worse results are produced than you would expect from this algorithm, but it still produces decent results for input sizes 15 and fewer. Altogether, the algorithm, it was a unique solution to the problem. It produces decent results for small enough data sizes, and it produces them in polynomial time. Now, I think the data sizes that it can accept is perfect because most playlists, you're not going to expect them to be greater than 15 to 20 songs long. So it will get very close to, if not exactly on the optimal result. In the future, I plan on looking into better distance approximation functions so that I can get better results from this algorithm. And I plan on using this algorithm to make my own playlists and make my own mixes. I think it'd be cool to use this and to see if it sounds as good as it should sound.